Hey everyone, welcome to our second week of HPC in the cloud. I'm Joe Schoonover from Numerics here in Boulder, Colorado. And today we're going to be doing the Fluid-Slurm GCP basics, where we'll show you how to stand up a HPC cluster, an auto-scaling HPC cluster on Google Cloud. And we'll walk you through some steps to customize it so that you can scale your compute resources to Google's global data centers. If at any time you have questions about any of the material we're covering, feel free to use the chat window to reach out to us, and we'll do our best to answer your questions as we go. We have a few getting started bits here to cover. First, if you'd like to follow along with the demonstration, we highly recommend that you go ahead and create an account on Google Cloud if you don't have one already. If this is your first time on Google Cloud, you can go to console.cloud.google.com and sign up with a Gmail account, or if you have a G Suite address, you can use that as well. And on your first sign up, you'll get $300 trial credit that you can use towards today's demo. You should expect if you're just following along with what we're doing today, that you shouldn't be spending any more than $5 to walk through the tutorial. Now, once you have an account, the first thing we're going to want to do is go to the Cloud Console, which is what I have shown up on the top left side of my screen, and we're going to walk you through enabling the Compute Engine API. So there's two ways you can do that. If you're going through the console, of course, if you have the G-Cloud SDK on your local system, you can use the command line interface there. But I'm going to walk you through doing this through the console. If you are up on console.cloud.google.com, if you look up on the top left, you have the triple bar navigation menu. It's also called the Products and Services menu. If you click through on that, you can either navigate down to Compute Engine and start there. If this is your first time visiting this page, you'll see something a little bit different than what mine's showing. It'll ask you essentially to enable the Compute Engine API. The other route you can go, again, in that Products and Services menu, you can scroll down to APIs and Services. You'll click on Enable APIs and Services. Go ahead and search for Compute Engine. And you see the product there, or the product marker for Compute Engine. Go ahead and click on that. And again, mine's already enabled, so it might look a little bit different, but you'll see a blue button that says the word enable there. Go ahead and click that and get that started. And the next thing we're going to want to do is set up identity and access management policies. Whenever you create resources on a Google Cloud project, you can control who has access to those resources by specifying these identity and access management policies. And essentially what these policies are is they align different roles and permissions with a cloud identity account or a Gmail or G Suite account. Today, we only need two roles attached to your account. One, you need Compute OS admin login. This is a role that will allow you to SSH into your cluster, and on Linux VMs in general, you'll be able to escalate to root privileges. And you also need the service account user role. To do that, we'll go to that Products and Services menu, go down to IAM and Admin, and IAM. Up on the top, you'll go ahead and hit Add, and you'll put your email address here. If you're doing this demonstration with some colleagues, you can also add them on here as well if they'd like to follow along on the same cluster with you. I'm going to go ahead and add myself. And then under the roles, again, we're going to need Compute OS admin login. Now you'll see there are two Compute OS login roles. One has the admin descriptor in the name. The other one does not. If you are creating, or if you're trying to grant access to people who you don't want to have root privileges on your cluster, you would go ahead and give them the Compute OS login role. For the stuff you're doing today in the demonstration, you will need root access, so go ahead and do Compute OS admin login, and we'll also do service account user. Okay, you can see it down there. Now I've already got mine set from last week's tutorial, so it's just going to show me that no changes necessary. Okay. Next up, you'll want to install the Google Cloud SDK on your system. So this is a command line tool that you'll be using today, really just to align SSH keys with your profile so that you can actually SSH into the cluster. So if you don't have the G-Cloud SDK, take a moment and go to cloud.google.com/SDK/doc/install. Go ahead and walk through the tutorial there and get that CLI set up on your system. And at the end of this, you'll run through the initialization process, which will authenticate that command line tool to use your credentials to work with your resources on Google Cloud. All right, so with that being said, the first thing, I know there's so many prerequisites here. The last thing we're going to do before we actually create the cluster is align an SSH key, a public key from your local system with your Gmail account or your cloud identity account. And like I said before, the way we're going to do this is using the G-Cloud SDK. So if you don't have an SSH key already, I'm showing you the commands here up in the top right. You'll use SSH keygen on Linux and Mac systems. If you're on a Windows system and you're using something like PuTTY, make sure that you're generating an SSH key that's an RSA type, and it has to be compatible with OpenSSH. So for those of you who are on a terminal, we'll just go ahead and run SSH keygen -t RSA. Now I already have a key on my system, so I'm not going to run this, but you'll go ahead and if you don't have an SSH key, you'll go ahead and run this as well. If you do have one, you can skip this step, but what you will want to do is attach that key to your cloud identity profile. So once you've installed the G-Cloud SDK, you've run through the initialization steps. Now what we need to do is align that public key with your account. So you'll do that with G-Cloud Compute OS login SSH keys add, and you can pass it a key file as an argument. If you're using the default path for the SSH key, on most Linux systems, it'll be in your home directory under a hidden directory called .sh, and then in a file called id_rsa.pub. Now again, I've already attached this key to my account from last week's tutorial. So again, I'm not going to run this, but if you're just joining us today and you haven't done this sort of setup before, you'll want to make sure you have that SSH key attached to your profile. As in the end, this is part of the mechanism that's going to authenticate you as being you, and it's going to allow you to get into your cluster. So I'm going to go ahead and clear that. So those are all the prerequisites, right? So you need to have an account on Google Cloud. You want to enable the Compute Engine API. You want to set the identity and access management policies so that you have Compute OS admin login and service account user roles, and then you want to attach an SSH key to your account. Now we can actually go through the process of creating the cluster. And the way we're going to do that is I'm going to show you a marketplace solution that we've developed and that's out there for everyone to use. Let me get back to that page. So again, we'll go to that products and services menu from the Google Cloud Console, and you'll scroll down to Marketplace. You can look for Slurm GCP or Fluid-Slurm GCP. And I'm just going to walk you through real quick the three different options you have here. So we've provided three different solutions that are really based off of different base images. So on the top, we have what I'll call classic Fluid-Slurm GCP. This is just a CentOS 7 HPC cluster that has Slurm 2002 installed and has environment modules, and it has some basic packages to help you get off the ground, Singularity and SPAC. Now we have the same exact thing except done on an Ubuntu 2004 system. And then on the bottom here we have Fluid-Slurm GCP plus OpenHPC. So this is identical to our CentOS 7 setup, except we have a number of pre-installed scientific applications available for you from the OpenHPC stack. We've installed software stacks using the GNU 8 compiler and OpenMPI. One of the sub-releases of version 3. So if you're looking for things like Trilinos, MFEM, Scalapack, those types of packages, NetCDF, HDF5, this is a really good place to get started if some of those packages are dependencies on some of the applications you want to run. For today, I'm just going to go ahead and use the classic Fluid-Slurm GCP CentOS 7 solution. You go ahead and click on that, and then we'll hit launch. So I'm just going to walk you through this form that we need to fill out, which is going to give you the starting point for your cluster. Now, everything we've designed is able to be customized after deployment, so nothing that we're going to do here is set in stone permanently, but we'll just make some decisions just to get us off the ground to run through today's demonstration. So the deployment name, you can call it whatever you want. I'm going to call mine Demo. This is a demo cluster for us. Essentially, this is going to identify the resources that we create in Google's deployment manager. And the name you put here is also going to be the prefix on the names for the login node, where your users will SSH into to interact with the cluster, and the controller that's going to host the Slurm job scheduler, the Slurm database, and some of those other resources. Next, you want to pick the zone that you want to deploy it to. Ideally, you're picking the zone to be something that's geographically close to you to minimize the latency for your connection to this cluster. Highly recommend looking through Google's documentation. They have a very comprehensive documentation that will show you where each of these zones and regions are. You'll notice, like for example, we see US Central 1, but you've got 4 different choices. So US Central 1 is what we call the GCP region, and then A, B, C, and F are different zones within that region, and all they really represent are just different data centers that are geographically close to each other in the US Central 1 region. I'm going to go ahead and pick US West 1B. So we're sort of out west. Technically, US West 3 is closer to us, but I don't know. I'm feeling like West 1 today. If you have non-default networking that you want to use, you can use this network drop-down menu to select that network. Now, the tutorial today, really, I'm not going to focus too much on any complicated networking, so I am just going to use the default setup here. We highly recommend when you do go to production, you think about developing a custom network that fits your organization's needs. So down below, after you have your network and your deployment name and the zone picked out, now we're going to figure out how we want to shape the login node, how we want to shape the controller, and then our first compute partition. Now again, out of the box, this is what we're going to get, and of course, after the fact, if we need to customize anything, my hope is that these kinds of tutorials that we do for you will show you how to make the cluster really yours. So first, you can have more than one login node. So if you've got a lot of users, one option for serving everyone's needs is to increase the number of login nodes you have available. On one side of it, you have multiple IP addresses you'll have to be sharing with folks, or if you're doing your own DNS routing to help people get access, just make sure you're aware that you're just gonna have to manage multiple access points. I'm gonna leave it as just one today, and now we're gonna get down to the machine types. So if you were to click on that drop-down menu, you'll see there's a lot of different machine types available on Google Cloud, and these are all the predefined machines. So you see we have N1s, and then you'll see standard, and then 2. So the way this works is that first, we'll call it a product code here. The N1, we have an E2, an N2, N2D. All these reflect different CPU platforms that you can have available. So we have like Intel Skylakes, and the N2s and the N2Ds are going to be in the newer models of the N2Ds are actually the AMD EPYC systems. But essentially, those product codes in the front reflect different CPU platforms. Now, on the far right side, that number that's left there is how many virtual CPUs are available on that predefined instance. Now, a virtual CPU is not a physical core. A virtual CPU is actually like a hyperthread. On an Intel platform, a virtual CPU just corresponds to a single hyperthread. So 2 virtual CPUs really gives you 1 core on the Intel platform. So just keep that stuff in mind. The other things to take into consideration here is there are performance limitations for file I/O, so both IOPS and bandwidth, and then network bandwidth as well. That's dependent on the number of cores that are there. Generally, we recommend at a bare minimum that you have at least 8 virtual CPUs, which gets you a fairly decent network bandwidth cap of 16 gigabits per second on the N1 systems. And I believe if you were to go up to this, I think it's the 16 core or the 16 vCPU instances, you'll be up to about 32 gigabits per second max bandwidth. Just, I think when you're thinking about designing a system for production, just try to think about what your users are going to be using these login nodes for. Most of the time, it's going to be like compiling code, text editing, interacting with the controller, things like that. So there are a lot of considerations, but today we're going to keep it simple. I'm going to leave it at standard 4 just for our demonstration. Then you also have you can choose the boot disk type and the boot disk size for the login node. Now, when you are on this cluster, the login node's actually not hosting the home directory. There's another directory called apps on the system that hosts the Slurm job scheduler, and it's a nice place to have software applications that you want to install and make available across the cluster. Home and apps are actually both hosted on the controller out of the box. And if you plan on hosting home and apps on the controller for the lifetime of this cluster, you might want to consider making that boot disk size on the controller a little bit bigger. And you might consider going towards like a more higher performance disk if you've got a lot of users that are going to hit that system pretty hard. Of course, our recommendation usually is like just keep these things the bare minimum and use other services like FileStore to host home and apps, and use things like Lustre to take care of your high performance file system needs. So again, today I'm just going to leave this at the defaults of 4 vCPUs and the 20 gigabyte disk size. Now we get down to the partition. Essentially, again, what we're going to be doing here is creating the first partition that'll be available to your users. And a partition is really just a grouping of compute nodes that you can gate the access to. You can control how long jobs run for, in these different groups. And the way we've set it up is where basically a partition can have groups of machine blocks that you can configure. And right now, all we're going to do is configure a partition with a single machine block. And then when we actually get on the system, I'll show you how we're going to customize that. We'll go ahead and give the partition a name. I'm going to call it demo. Let's call it demo partition. And you have two options here, the static node count and the max node count. So the static node count is the number of compute nodes that are going to be created out of the box, and they will live on forever. They're not going to be these auto-scaling nodes. For a lot of the work that we do on the research side, we just like to keep our login node and controller going 24/7, and then just let the compute nodes come up whenever we have jobs. So I generally keep that static node count 0. The upshot with having a static node count of 0 is you're really not paying for those compute nodes when you're not running jobs. The downside is when you first want to wake those compute nodes up, it can take like 30 to 60 seconds, but compare that to most queue times on HPC clusters, that's actually not a bad deal. The max node count is the maximum number of nodes that this machine block can burst out to. Again, I'm just going to leave defaults here, so we're going to have 0 static nodes. Everything's going to burst as needed when we submit jobs, and we'll only allow up to a maximum of 10 nodes to be launched. Again, the machine type, I'm going to drop this down to standard 2s just for the demonstration. If you've got a particular application in mind, if you're doing like tightly coupled MPI jobs, things like that, the higher core count systems are the way to go, because the more you can keep on a single VM, the lower the latency is going to be. So if you're thinking in that realm, definitely think of your higher core count systems. And reach out to us if you have any questions about where would be or what machine type or shape you should use for your application. We'd love to help you out. So I'm just going to do standard 2s here. Now you can select GPUs. If the zone you've selected supports GPUs, you can have up to 8. And you've got a variety of NVIDIA GPUs available at the moment. I'm not going to do any GPUs today, but in future tutorials we'll be talking a little bit more about GPUs. And same thing with the login node and controller, you have boot disks to work with. If you need like local scratch space on compute nodes, you can either use these boot disks, or if you come down, you can actually attach very high performance local SSDs. You can go with up to 8. Each of these local SSDs is 375 gigs, and our system will fuse all those disks together into a single RAID 0 configuration, so you can end up with a few terabytes of incredibly high performance local scratch disk space. So if you're doing things like machine learning, where you have a lot of file IO you've got to do, local SSDs are a good route to go. All right, so once you've made all your decisions, we'll go ahead and hit deploy. Essentially what's happening now is we've put in a request to Google to go through and create this login node and the controller. And those virtual machines are being launched with the images that we've created that have all the software you need for running Slurm. And like I mentioned before, we have environment modules, and then we have Singularity and SPAC available. Now, if you were to draw a parallel to like what this typically would be in on-premise HPC world, this is like the procurement side. You've decided what size and shape of your system you need. You've essentially clicked go. You're telling Google, yes, I'm ready to use this. Now, the nice thing is you're not actually having to physically set up the hardware. All the software we have is already set up for you. So we really wanted the system to be something where anyone can click it and go without necessarily needing extensive system administration training to just get off the ground. Now, certainly when you go into production, it's nice to have that separation of labor where you have your researchers doing researchers and system administrators really keeping that system running for everyone else. So what's going to happen next here, let me go ahead and advance my slides, is we're going to go ahead and SSH into this cluster once it's made available. And we're going to, I'll show you how to poke around a little bit and see, again, we'll take a look at the partition we created, and I'll show you how some of the home and apps directories are mounted in this cluster, so you just get a feel for what you're getting into. Now, if this is your first time using OS Login or really any third-party SSH tool to get into Linux VMs on Google Cloud, your Linux username is going to be a little wonky. Essentially, it's going to be your email address, your entire email address, including the domain, except you're going to replace the @ symbols and dots with underscores. So, for example, someone@gmail.com is going to be someone_gmail.com. And if you're a G Suite user and you haven't configured your POSIX username information, like for me, it's joe@FluidNumerics. FluidNumerics.com. My original username on these Linux systems was joe_FluidNumerics_com. Now, if you are using the admin SDK, or if you're familiar with using the admin SDK and the directory API, you can actually customize all of that. You can change your POSIX username, you can change your home directory, UID, GID, you name it. You can control it through the admin SDK. And you'll see, so when you see me log in, you'll actually see my username is just Joe. It's the same username I have on my other systems. So once your deployment is ready, you'll see a page that looks like this. You'll have the IP address for the login node and an IP address for the controller. I'm also going to go ahead and open up the Compute Engine API so you can get another view of the resources we've created. So again, go to that Product Services menu and look down for Compute Engine. And on that Compute Engine page, you'll see, once this loads, we've got demo login and demo controller, again with those IP addresses. Okay, so I'm going to copy that IP address, and we'll go ahead and hop into this instance and take a look around. Whoops, there we go. Cool, so once you get in, you should see the Slurm logo. And don't worry about this. This is just a benign error if you haven't configured Linux groups on these instances before. The operating system will throw a message like this, but it's nothing to be worried about. Okay, so if you were to run SInfo, you'll see that demo partition is available. The asterisk next to that name indicates that this is the default partition. We have 10 nodes available, and they're in an idle tilde state. So whenever you see the tilde, this just means it's in what's called a cloud state, which means the controller knows, the Slurm controller knows that these nodes can be provisioned when needed. And then, of course, we got the names of those, the nodes in that partition. If you run df-h, you can see, again, the apps directory I mentioned before is hosted by the controller, as is home. And if you're curious about what modules are available out of the box, you can run module avail. And you can see we've already actually got Python 2 and Python 3 installed for you underneath apps. And the reason why we've done that is because if you want to install Python packages globally for your users and have them available on compute nodes, they need to be in a place that can be NFS mounted to those compute nodes. And apps absolutely meets that criteria. So if you want to have Python packages available to all your users, just module load one of those, and then you can run pip or conda or whatever Python package manager you're using, and it will install those packages underneath the apps location. We will have another tutorial on all sorts of package management because that really deserves its own block of time to talk about. Okay, so from here, what we want to do is let's just run a simple job. But in order to run a simple job, we actually have to add ourselves to the Slurm accounting, so we're allowed to actually do that. So you're going to need to go root, and we're going to use a tool that we've provided on this cluster called Cluster Services. This is a command line interface that allows you to really customize your cluster to meet your needs. So go ahead and go root sudo su, and you'll know your root because this will change to a hashtag, and you'll see root at on the front side there of your shell. So Cluster Services does have a help file, so if you just run cluster services -h, you'll see all the commands that are available to you. We're certainly not going to cover all of them today, but I'm just going to walk you through a little bit of a workflow that you can generally use for updating your Slurm accounting. You can apply the same workflow to updating your mounts, so NFS file systems, Lustre, Google Storage buckets, those types of things, and then your partitions. So first we're going to start with just updating the Slurm accounts. So to get everything is controlled in cluster services and on this cluster through what's called a cluster config file, which is a YAML dictionary that describes your cluster. If you want to ever see what your current cluster configuration looks like, you can just run cluster services list all. I'm actually going to forward this output to config.yaml. We'll open up config.yaml and take a look inside. There's a whole bunch of information here that describes the compute images you're using, which, surprise, future tutorial, we're actually going to be showing you how to bake your own custom images for your applications and swap them out on this cluster so you can have all your applications installed that way if you wanted to go that route rather than doing a centralized installation underneath apps. So there's a lot of ways you can do things. We definitely believe in flexibility at Fluid Numerics. Let's scroll down here. We've got our partitions. What we're really interested in right now is the Slurm accounts. But the Slurm accounts field is just an empty array right now. So what we need to do is use another one of the cluster services commands. I'm going to go ahead and bump that down to the bottom. We're going to use one of the other cluster services commands to give us a sample block of the Slurm account dictionary. So we'll use cluster services sample Slurm accounts, and then we'll append that. So you'll use the double right carets to config.yaml. So open that up, and now you can see down below we've got a sample block for Slurm accounts. Let's go ahead and clear that empty array specifier there. So the Slurm account's pretty simple. You need to give a Slurm account a name. Since I'm sticking with the theme here today, we'll call it demo account. And then the partitions, you want this group of users that are in this Slurm account to submit to. You'll go ahead and add here, so we can say demo partition. Whoops, let me spell that correct. And I'm missing another I. There we go. And we'll verify all this stuff before we apply any changes. And then you can add your list of users. So again, these will be your Linux usernames. So even with the ugly _gmail_com, whatever your Linux username is, you'll add that here. I'm going to add Joe. Guy's also on our team, so I'll go ahead and add him here. And let's write that. Now, we generally recommend that you preview any changes before you actually apply them, just so you can make sure that everything is looking right. So we can do cluster services, update Slurm accounts, config is config.yaml. You'll always want to pass it whatever config file you're locally working with, otherwise you won't have any changes actually applied. And then we're going to add the preview flag. So what it's going to do is it's going to compare against the current cluster configuration and tell you what the differences are with this config that you've passed here. You can see now it's going to add our first Slurm account block. We're going to allow them to submit to the demo partition. The name of the account is demo account, and we've got users Joe and Guy on that list. Let's double check that we've got the spelling right on that partition. And it looks like we're doing good. Okay, so we can go ahead and run that command now again, except we can remove the preview flag. We'll give it a minute. Okay. Now, if you were to use the Slurm S Account Manager command line tool that comes with Slurm, you can list the users. And you can see now we've got Guy and Joe underneath the demo account. Cool. And the other nice thing is Guy and Joe now are both authorized to submit jobs to that partition. The only other person that can submit to any partition is root. So it's a good way to gate access to different resources if you need to have that kind of permissions control within your Linux system that's sort of outside of the scope of identity and access management privileges. So we'll go ahead and exit, and I'm going to show you how to run just a simple, what's called a job step to the cluster. So you're going to use the srun command, pass it the -n flag, and n stands for the number of tasks. We'll say we're going to run one task, and by default, one task is assigned to one virtual CPU on our systems. We want to tell it what partition to submit to. Now, if I didn't tell it because the demo partition is the default, that's what it would select, but I like being overly redundant, so I'm going to go ahead and specify the partition. And then you also need to give it the account you want to use. So if you have users that are aligned with multiple accounts and you're doing your back billing or whatever that way, it's important to let your users know what accounts they have and what those accounts should be used for if you have different projects y'all are working on. So we'll say demo account, and I'm just going to run hostname so that basically, whoops, I have a invalid account or account partition specified. I messed up somewhere. I was a little hasty. Well, I'm going to cheat just so I could show you what's going on here. What is happening? Let's go back and take a look at what we did. This is the wonderful thing about doing this stuff live, is just about anything can go wrong. Let's take a look at that. We've got demo partition in there, a demo account. Huh. That's really weird. Sometimes, let's give this another go. Okay. Yeah, I'm not sure what happened. I think I might have gotten a little sloppy here. I think we'll be able to correct it on the next go around here. But just to show you what happens when you submit a job, essentially what happens is the Slurm controller will say, hey, this compute node is not currently available, but we know it's in this cloud state, so it issues calls to Google Cloud to go provision that compute node, and you can see on the Compute Engine UI that compute node is being provisioned for us. Now let me find the right screen here. Now the deal is when that request is made in the back end, we're basically getting those compute resources. We're launching our compute node image on that, and the system is booting up, and we're waiting really for what's called the Slurm daemon to start. Once that Slurm daemon is able to start communicating with the controller, and it's authenticated to say, yep, I'm ready to take a job, your job will actually start. And then this can take, on our CentOS images, anywhere from 30 to 90 seconds, which, if you think about, again, if you're running on premise, this is fairly typical queue times for like debug queues and stuff like that. And the nice thing is, if you really wanted to have a higher max node count, Google has tons of resources available, so that, if you had, 50, 60 users that you wanted to accommodate, Google certainly has the resources to be able to do that and keep those queue times incredibly low. And so you can see now down on that terminal window, the host name is reported back from that instance, and the demo partition 0 node is just completed. Now, the cool thing is, as long as that compute node is up, I can run that job again, and it comes back immediately. So the deal is, those compute nodes will stay live, and our default is 5 minutes. So the node will stay live for 5 minutes while it's idle. If it's idle for longer than 5 minutes, the controller will automatically tear it down for you. Now, in that config.yaml file, if you wanted to change that setting, you'll see that suspend time. You can drop that down. You specify in seconds how long you want those nodes to stay idle for before they're torn down. So what we're going to do next is we're going to customize the compute partitions to deploy compute nodes into multiple GCP zones. Now, to update compute partitions, you do need to be in the on the controller. There's a few reasons why, but essentially what's going on in the background when we make these changes is the controller daemon and a few other resources need to be restarted once we update the partitions. So we'll go ahead and log out from the login node, and let's go to that console and grab the controllers. That's the login node. I want the controllers IP address. So we'll go ahead and SSH into that system. Okay, and you'll see a very similar startup screen. And because the controller hosts that home directory, that config YAML we are working with is already there. Because we're going to be working with cluster services, go ahead and go root. All right. And next thing we're going to do is open up that config YAML, and we're going to mess with the partitions. What we want to do here is expand resources to cover multiple zones here. So you'll notice right now everything in our in the console up on the top left of the screen, you'll see that column for zones. Everything is in US West 1B right now, which means everything's being deployed in the same data center. Now, while this is a more ideal scenario to have like all your jobs and everything in the same data center in terms of like communication latency, if you want to have some type of redundancy in case of a zone outage, or if there's maybe a data center is at capacity at the moment and you want to easily spill over into another nearby data center. So operating within in another zone in the same region turns out to not be terrible for performance. I mean, it's certainly not as ideal as being in the same data center, especially for those tightly coupled applications that use MPI. But this is not a bad fallback, just so you can keep things running seamlessly. And so the way we're going to do this is we're going to keep everything in the same partition, but we're going to add another machine block. So you'll notice we got underneath partitions in the config YAML. There's a number of things you can specify, but you see we have this machines block, which is an array of items that specify what machines are available. I'll turn on my line numbering here so this starts to make a little bit of sense. But from line 25 down to line 39, we have one machine block specified. So I'm going to go ahead and copy that. So we'll grab those 15 lines and we'll paste it down below. Okay. Now, what I want to do is right now I have the first machine blocks in West 1B. Let's say I want to add one in West 1C. So you can just change the zone, but you also are going to want to change the name of the resource. What I usually recommend is you'll have, when you name your systems, you'll pick something on the front end that might describe how many cores are available. So we might say N12, or let's say N1-2. And then we'll say the zone it's available in, so US West 1C. Okay, so we'll do the same thing up here, N1-2, and then we'll say US W1-B. Okay, so that's really it. All we're doing is changing the names, and we're going to change the zone. All right, so we'll run cluster services again. This time we're going to do update partitions. And we'll pass it a config And we're going to preview first. Okay. So what it detected was one that in the first partition, so partition 0, machine 0, we're going to change the name. And then we're going to add another machine block. And now the only thing we're really changing relative to that first machine block is the name. It's N12 USW1C and the zone, which is US West 1C. So we'll go ahead and I think this is looking good. So we'll go ahead and apply this. All right. So it's going to update our partitions for us. Now if you run SInfo, we got demo partition. Now we've got 20 nodes available, some in West 1B and now some in West 1C. Now if you look back at your console, you still have this demo partition 0 up here. Now the deal is, if you've changed your compute partitions without letting the controller spin down these compute nodes for you, this node is no longer under the supervision of the controller. So you'll actually want to delete that manually if it didn't spin down automatically for you already. So we'll go ahead and click the checkbox next to demo partition 0 and hit delete. Make sure that it is demo partition 0. Don't delete your login or controller. All right, so that's going to go ahead and spin down. We're on the controller. While we're here, I'm gonna try to refresh our Slurm account. So I'm gonna delete these this last block here. So we got 64 down to 69. I'm gonna just hang on to those. We're gonna remove our Slurm accounts and then we're gonna add them back in just to make sure we didn't mess anything up on that first go around. Again, we'll preview. All right, so so if you're ever curious what happens when you try to remove items, you'll see now it's highlighted in red. So this is actually nice for you to see this happen. Okay, so I think that's all right. Go ahead and do that, and then we'll add ourselves back in. Sometimes these things happen. All right, let's open up that config again, and we'll put that block back in the bottom. So we've got our Slurm accounts. Again, demo partition, demo account. We got users Joe and Guy. Should be okay. Again, we'll preview just to be sure. And we'll run SInfo again, make sure the spelling on everything is correct. 'Cause if you don't get that right, it will be problematic. But I think we're okay. I'm not sure what happened there. All right, we'll go ahead and apply that change, and then we're going to hop out of the controller here, and we'll spin up a couple jobs from the login node. All right, let's get back into that login node. Okay, and I think I see what happened. Okay, so we'll use that srun command again. This time we're going to do 2 tasks. Okay, and then what I want to have happen is I want to have one task run on each of these different zones. So there's a number of ways to specify task affinity with Slurm. The easiest one for this case is just to say n tasks per, n CPUs per task. We're going to set to 2 here. The reason why we're going to set it to 2 is because there's 2 virtual CPUs on each node. So this will give us 4 vCPUs spread across 2 of our nodes here. So we'll say n CPUs per task is 2. And then what do we want? We want the partition is demo partition, and the account is demo account. And then now we can just give it the command we want to run, which is hostname. Whoops. Oh, sorry. It's n tasks per node. Boy, today is just not my day. There we go. N tasks per node. Sorry about that. So we're going to run 1 task on each node. So I think I guess to fill you in on what happened here with the Slurm accounting is, I think I logged onto the login node a little bit too early, and the home directory hadn't quite synced when I had first gotten on. When I was trying to search back through for the srun command, my bash history wasn't populated. So anyways, if you ever experience something like that, usually just logging out, logging back in, and refreshing does the trick here. Everything is runs on timers. All right, so now the deal is we've got these two nodes coming up. Oh, you got everything in West 1B. Let's go ahead and let's just up this. Let's run my N4 here. We'll refresh that screen. There we go. Now we've got some compute instances kicking up in West 1C. So we'll let those spin up. And while we're waiting for that to happen, let's talk a little bit more about why we'd want to deploy to multiple zones. So like I said before, Google has data centers worldwide. Those data centers are grouped in what are called regions, and a region is just a set of data centers that are geographically close to each other. Now, most regions have 2 or more zones available, and sometimes there can be data center outages, or there might be a data center that's really seeing a lot of usage. And the idea behind having resources quickly available in multiple zones in the same region is still to keep your jobs running geographically close to each other, but to give you that extra capacity to spill over very quickly into some of Google's other resources. So it just, for your users, this prevents things like downtime, long waits in the queue, or just some frustrations with jobs actually going through. So being able to easily and quickly leverage all the compute resources that Google has to offer is a huge benefit we see to having this sort of customization available on your system. So now you can see we've got everything's responding in West 1B and C. And again, because those nodes are already live, right? Here, like the jobs go through right away. We can go ahead and skip this next slide. I thought we were going to have a little more time, but things were just moving a little weird for me today. All right, so what we're going to do next is let's say you've got just a lot of compute to do, and you just need massive amounts of compute cycles, or you might have a controller and a login node deployed in a region where you might not have GPUs, and you do need to have compute resources kind of stationed around the world where those GPUs are available. So we're going to make some customizations to add compute nodes in another region. So here right now we're working in US West 1, which is over in California, and we're going to add compute nodes in another region in Europe. So again, we'll hop out of that login node, go into the controller. Okay, and because we're going to use cluster services, you can go ahead and go root. Open up that config YAML. All right. And we're going to take that last machine block that we copied. So I'll set number. So from lines 40 down to 54. So we'll snag those 15 lines, copy, and paste below. Now once you pasted, we're going to change the zone. So we're going to say Europe, West 1. And let's put it in West 1B. The name, we'll change the US to EU and the C to a B. Now the other thing you need to do is change the VPC subnet. So the deal is the way the networking works on Google Cloud is you have all your compute resources deployed in a virtual private network. Inside that network you have subnets, and a subnet can only be defined for a given region. So since we're going multiple region here, we actually have to have another subnet. Now, if you're using the default networking, the easiest, becomes really easy, is you can just come over here to the VPC subnet, and you can see the URL. We have projects, the project ID that's hosting the subnet, and then you'll have the region that you can specify. So you'll come in here and change that to Europe, West 1, or whatever this other region is that you're deploying to. Now, if you're using your own custom network, just make sure you have a subnet available in that other region as well. We do have some Terraform modules that help you do multi-zone, multi-region out of the box with our images as well. So if you are interested in learning how to use those, we'll be doing some tutorials on those Terraform modules in the coming weeks. All right, so with that done, we're going to run through the usual. We're going to run cluster services. we're going to update the partitions, and we're going to run through preview first just to double check our changes. All right, so now we see we've got another machine block. We want to go in the Europe West 1 region so that VPC subnet looks good. The zone is Europe West 1B, and the name, we got N12 EU W1B. All right, that's looking all right. Let's go ahead and apply that change. And so in the background, some of these configurations are changing and the controller daemon is restarting. Let me clear my screen here and run SInfo. And now you can see, so it looks like these 4 nodes are actually powering down, those 4 compute nodes, which is cool. Does that automatically for you. And now we've got 26 nodes in the idle tilde state, and these 4 are powering down. But now you can see we've got something in Europe West 1 in addition to our nodes in California. All right, so let's go back to that login node, and we will run a job across all those. So if I pull up that srun command again, I'll say 6. Okay. Now, because so I guess what I wanted to cover here really is just let you know you can choose the node you want to run on, and that's really where this feature starts to shine. Let me run that SInfo command so I have, for reference here, the names of these nodes. I'm not going to trust myself to spell it correctly today. So if you add the node list modifier flag to srun, you can give it the list of nodes you want to select from, which again is nice if you're currently just looking to move some of the compute to another region. If you have all these nodes already specified in the same partition, you can easily just specify, you know, this entire name down here, or some of these guys. But specifically because I want to distribute these across multiple regions here, what I'm going to do is I'm going to tell it 3 tasks, 1 task per node, and I'm going to give it N12 Europe West 1B 0. I'm going to give it the US West 1B 2 and the US West 1 C2 as the node list. So we'll say N1 to EU W1B dash 0, N1 to US W1 dash C, and we'll say 2, and then we'll do the same thing for West 1 West 1B. All right, so you've given it the 3 nodes. We want 1 task per node, 3 tasks, and we're just going to print the host name. Invalid node name specified, and that's because I forgot the number 2 at the end. Of course I would. All right, so let's go ahead and refresh that screen. So you can see that Europe node is coming online, and then we've got the US West 1 B2 and US West 1 C2 coming online as well. So we'll give that a minute to spin up and provision the Slurm daemon and connect. And while that's happening, let's talk about the multiple region reasoning here. Common theme you'll hear me say, right? Google data centers are worldwide, and those data centers are grouped into regions that are essentially groupings of data centers that are geographically close. And there are some cases, if you're processing lots of data for like high throughput computing type jobs, where you really just want a massive number of GPUs or a massive number of cores to get through whatever it is you happen to be doing, having the ability to scale out to multiple regions really gives you full access to an enormous amount of compute power that Google has to offer. And so this is really one of the biggest reasons we see to have multiple regions there. Now, there are some caveats here. Once you have nodes in multiple regions, the communication latency between 2 different regions is incredibly high in comparison to the about an order of magnitude higher than the communication latency in a single region. So things like MPI jobs, you probably don't want to be distributing MPI workloads across multiple regions simply because you're going to see the hit in the MPI communication performance. Additionally, file IOs, if you have file servers that are in different regions from these compute nodes, you're going to see a hit in your file IO performance. So in some cases, it's necessary to have multiple file servers serving each of the regions where you have compute nodes. Or of course, if you're using essentially scratch space on your compute nodes, if that's really the type of workflow your application needs, and you can get around it, then that's cool. But just keep in mind that any time you have to cross the network between regions, you're going to see a performance hit, whether it's MPI, whether it's file IO. So, we generally recommend as a best practice, keep your MPI jobs within the same region and ideally within the same zone. There are a few blog posts from Google that actually talk about how to do really tight placements of Google Compute instances if you're really going for the most ideal performance. But of course, I'd say the bare minimum, keep everything in the same region. If you're doing MPI, ideally same zone. And if you do go multi-region, think about where you're placing your file servers. So now you can see all the nodes have responded. And you can see the Europe West 1 node responded last. And again, that's because of that latency issue. So if I ran this again, you'll see the US West 1 nodes respond almost immediately, but it takes the Europe West 1 node a little bit longer to respond. And that should give you some idea of the latency difference between those, between communicating within a region and between regions. All right, so now that all of this is, we've gone through how to get this cluster off the ground, how to do these kinds of configurations that give you access to all the compute resources that Google has to offer. That's really it for the demo today. So we're going to go ahead and tear down the cluster. So I'll show you actually how you can power down nodes. This is just useful knowledge to have when you're managing your cluster. You can use the scontrol command from the Slurm package to power down those nodes, which will essentially, in the back end, there are already tools in place to handle this sort of power down through Slurm's power save module with Google Cloud. So you'll run sudo. If you use -i, this will forward your current environment through, so the scontrol binary is in your path. So say update node. We'll give it the node list. So we had n1-2 -us w1 b-2 n12 us w1-c-2, and then we had n12 EU w1-b-0. Those are the nodes we want to update. We want to put them in a power down state so that they're taken down for us. So now if I go back to that console, you can see they're all being spun down. Now the other thing you want to do is go to that deployment manager page and delete those login and controllers. Of course, if you're leaving your cluster up and you're ready to do more things, you can leave it up. But that's about it for today's demo. If you have any questions, I'm more than happy to stick around for a few minutes and answer them. So you can use the chat window in the YouTube live stream page. I'd be happy to answer any questions you might have about this tutorial, but future tutorials, anything you might want to see in the future, we'd love to hear your feedback. So we want to hear how you're trying to do HPC in the cloud, and we want to help you get there. While you're thinking about what questions to ask us, I'll share with you a few community resources that we've put out there that should help you find a lot of the information we've talked about today. You can go to our help site, help.fluidnumerics.com. You'll find the Slurm GCP page, and you'll find a lot of the stuff we've done today. There are some code labs available where there are some code labs for walking through the multi-zone, multi-region deployment. There's also code labs on package management, Python package management particularly. And anytime you need support, if you're using any of our solutions, just reach out to Fluid-Slurm GCP at fluidnumerics.com. That is the best way to get a hold of us if you ever need help using our solutions. All the communications we have here go to a public Google group so that the community can benefit from the responses that we provide for you there. And of course, a shameless plug to join us again. We do this every Thursday at 4 p.m. Mountain Time and Fridays at 9 a.m. just in case you're more of a morning person than an evening person. Next week we'll be picking up some new material. We'll be moving away from doing these basic live streams for a couple weeks. But feel free to subscribe to our YouTube channel. Keep track of us at our help page. We have our calendars listed underneath the Slurm GCP Live Community Training page on our help site. So with that in mind, thank you for joining, and we hope to see you next time.